Welcome to Department of Botany, Kalna College. Myself, Dr. Somnath Mondol. Today's topic is Phyllotaxy. Stems are divided into nodes and internodes. Foliage leaves remain sprayed on the stem with long or short internodes. This arrangement is called colline. However, in some cases, leaves may arise as a cluster or a rosette from a very short condensed stem just on the top of the root, like in radish, and this type of arrangement is called radicle. In colline arrangement, there may be 1, 2, 3 or more leaves arranged at each node. Phyllotaxy is the mode of arrangement of leaves on stem. Now, suppose this is a stem and it is divided into nodes and internodes. Phyllotaxy can be divided into two main types. One is cyclic phyllotaxy, another is acyclic or alternate or spiral phyllotaxy. Cyclic phyllotaxy is again divided into opposite and verticillate phyllotaxy. In case of opposite phyllotaxy, there are two types: opposite decussate and opposite superposed. Let's discuss each type. Cyclic phyllotaxy. In cyclic phyllotaxy, leaves are placed on a circle at each node and the angle between adjacent leaves are the same. Therefore, if two leaves in a node, then the angular distance between these two leaves will be 180 degree. Similarly, if three leaves in a node, the angular distance will be 120 degree, and so on. If four leaves in a node, it will be 90 degree. So in this diagram, a node is equivalent to a circular region, that is all over it is 360 degree an angle. Now if two leaves are present on a circle, then they are 180 degree apart. If three leaves are present in a node, then they are 120 degree apart from each other. Now, opposite phyllotaxy is a type of cyclic phyllotaxy. When leaves are arranged at each node opposite to one another, it is called opposite phyllotaxy. Therefore, the angular distance between leaves will be 180 degree as there are two leaves at each node. Opposite phyllotaxy is again divided into opposite decussate and opposite superposed phyllotaxy. First, opposite decussate. If successive pair of leaves are placed at right angle to one another, it is called opposite decussate phyllotaxy. Therefore, when looked from the top, leaves are found to be arranged in 4 vertical rows. For example, in Calotropis procera, Asclepiadaceae family, or in Rubiaceae family, Ixora, Catharanthus roseus of Apocynaceae are some common plants around us which display the opposite decussate type of phyllotaxy. Let's have a picture. So this is the first pair of leaves at the lowermost node. Then another pair of leaves just above, and look at that, the position is rotated. How much? by 90 degree. Again, next pair of leaves on the upper node, it is again 90 degree rotated. So when look from the top, we can see the stem. Then in two rows there will be the lowermost leaves, the uppermost ones will be just at right angle to the lowermost, then the smaller or younger leaves again at right angle, and then again at another right angle. Therefore we can find there are 4 vertical rows of leaf arrangement in case of opposite decussate phyllotaxy. This is Bryophyllum sp, where you can see opposite decussate phyllotaxy. You can easily see that the 2 pair of leaves are present apart by 90 degree angle in between nodes, and the younger leaf pair that is coming out from the apical bud is again at 90 degree of the next leaf. Next category is the opposite superposed phyllotaxy, where successive pair of leaves are placed in one plane, that is exactly on top of one another. Therefore, when looked from the top, the leaves are found to be arranged in 2 vertical rows. For example, Combretum indicum of Combretaceae family, Syzygium cumini, the Myrtaceae family. This is Combretum indicum. Look at that. At each node, the leaves are just at top of one another. The leaf pairs at top of one another. Therefore, there will be 2 vertical rows of leaf arrangement. So, this is the lowermost leaf pair, then the above, and then the another pair at the topmost. Therefore, all the 3 pairs of leaves in 3 nodes are one above another. Therefore, when look from the top, we can see there are only 2 rows, and on these 2 rows all the leaves are arranged from younger to older, from top to bottom. Or if we consider from bottom to upward, then we can see the lowermost will be the most edged leaf, and the youngest one will be at the top. However, there are instances where the arrangement of leaves is initially opposite decussate, but later it becomes opposite superposed. For example, in Psidium guava, a seedling shows opposite decussate phyllotaxy, but as it matures, the stem becomes flat and the phyllotaxy converts into opposite superposed. Next is the verticillate phyllotaxy. So in case of opposite phyllotaxy, we have seen there are 2 leaves at each node. But what happens if more than 2 leaves are there at each node? Then it is called verticillate phyllotaxy. For example, in Nerium oleander, there are 3 leaves at each node. In Alstonia scholaris, another member of Apocynaceae, there are 5 leaves at each node. And this is the image where we can see there are 3 leaves at each node. So this is verticillate phyllotaxy. Next, acyclic or alternate or spiral phyllotaxy. In this type, each node bears only 1 leaf, and thus the angular distance between 2 consecutive leaves will be constant. So it is not going to be haphazard. It is the angular divergence, the angular distance between consecutive leaves will be constant in plant to plant. When looked from the top, the leaves are found to lie in a fixed number of vertical rows. And these vertical rows, as we have seen, in case of opposite decussate, there are 4 vertical rows. In case of opposite superposed, there are 2 vertical rows where leaves are arranged. But in case of acyclic or alternate or spiral phyllotaxy, the number of vertical rows in which leaves are arranged will be varied from plant to plant, from genus to genus. So these vertical rows are called orthostiches. If number of orthostiches is 2, it is called disticus. If 3, it is called tristicus. If 5, it is called pentasticus, and so on. The angle between adjacent orthostiches will be constant. To correctly understand the plan of a spiral phyllotaxy, we can imagine a line touching the bases of successive leaves, and this line is called genetic spiral. The angular divergence can be calculated by the following formula, that is, number of circles covered by the genetic spiral from a particular leaf base to the base of another leaf present exactly above the first leaf, divided by total number of leaves or number of orthostiches present in between into 360 degree. So we will discuss with some examples so that it may be more lucid, more easy. First of all, let's have a diagram. So here will be 1 leaves per node. So there are 1 leaves per node, like that. And we can draw a spiral line, or we can imagine a spiral line touching the leaf bases, and this spiral line is called the genetic spiral. And the genetic spiral, look at, from 1 leaf to another and then to another, falling just above the lowermost leaf. So it is a full circle. So it is covering a full circle, 180 degree to the first leaf and another 180 degree back to the second leaf. That is a full circle, 360 degree. So that is why we can count how many circles a genetic spiral is taking to come to the just above leaf, starting from our leaf 1. So here is an example of Bacella leaf, where we can see the alternate phyllotaxy. Now an example of alternate, that is disticus, where we can find 2 orthostiches. It is also called a half phyllotaxy and is common in Cyanodon dactylon, that is the Durbaghas. Now look at that. So on stem, this is disticus phyllotaxy, where 1 leaf at each node. So let's count. Let's start from the lowermost. So look at that. There is 1 line, 1 vertical row where 3 leaves are present, and there is another vertical row where 2 leaves are present. Therefore there are 2 orthostiches, orthostiche 1 and orthostiche 2. In 2 orthostiches or 2 vertical rows, all the leaves are arranged. That is why it is called disticus. Now draw the genetic spiral. So here we can see that the genetic spiral is taking a complete turn from leaf 1 to the leaf just above. Exactly above the leaf 1 is 1 circle, 1 complete circle, that is 360 degree. And in between there are 2 leaves. So now we can calculate the angular divergence. So number of circles covered by the genetic spiral divided by number of orthostiche or number of leaves in between. So number of circle covered by genetic spiral is 1 and number of orthostiche or number of leaves in between is 2. So that is why we say this is half phyllotaxy, 1 by 2. So what will be the angular divergence? Into 360 degree, and it will give us the data 180 degree. Therefore, the angular divergence here is 180 degree. Similarly, so let's have a look at the picture. So this is cyanodon-dactylon disticus phyllotaxy showing. Okay. So next we are coming to the tristicus or 1/3 phyllotaxy. It is also seen in another grass, that is Cyperus rotundus, and as the name suggests, there will be 3 orthostiches. So let's have a look. First, identify the orthostiches. So 2 leaves are present in one orthostiche in the image, another leaf in another orthostiche, and third orthostiche there is another leaf behind the stem. Stem is in front. Okay, look at the image carefully. Therefore, there are 3 orthostiches. Orthostich 1 with 2 leaves, orthostich 2 with single leaf, orthostich 3 with a single leaf behind the stem. Therefore, there are 3 orthostiches, and thus it is called tristicus. So let's draw the genetic spiral from leaf 1. So if we can draw the genetic spiral, then we can see from leaf 1 to the leaf exactly above the leaf 1, there are how many leaves? There are 3 leaves. And there are how many orthostiches? There are 3 orthostiches. So genetic spiral is taking a complete turn, and in between it is covering 3 orthostiches or 3 leaves. Therefore, number of circle covered by genetic spiral is 1, divided by number of orthostiche or number of leaf is 3. So that is why it is called 1/3 phyllotaxy into 360 degree. So the angular divergence will be 120 degree. So on we can calculate the tristicus, pentasticus, octasticus, all these different types of phyllotaxies. For example, in hibiscus rosa sinensis, pentasticus or 2/5 phyllotaxy is found. So the genetic spiral has to cover 2 full circles to get to the leaf just above the first leaf, where we are starting the count, and there will be 5 orthostiches in between, or there will be 5 leaves in between. So that is why 2/5 phyllotaxy in hibiscus. In Carica papaya, there is octasticus or 3/8 phyllotaxy. There are 8 orthostiches. So thus, these fractions of common type of phyllotaxis can be arranged in a series, where additive result of numerator and denominator of any two gives the fraction of third. Let's have a look. So first of what we have studied is disticus 1/2, then tristicus 1/3. Now coming to the pentasticus. So just adding disticus and tristicus by numerator and denominator, 1 + 1 divided by 2 + 3 equal to 2/5. Next one. So next one should be 1/3 plus 2/5 added by numerator and denominator. So this is going to be 3/8. So let's have a look. So this is octasticus, 1 + 2 divided by 3 + 5. So we are adding previous two, getting the third one. So in this way we can get the following phyllotaxis. So what is going to be the angular divergence? So this is called the Fibonacci series. And however, we all know about the palm trees, where we can see that there are crown of leaves at the stem apex. So what about this? In case of palm tree, the internodes are so condensed that the leaves are placed like a crown at the apex, at the apical region of the stem. So this type of phyllotaxy is called parasticus phyllotaxy, where the exact number of orthostickies or the angular divergences can be very hard to calculate. So this is called parastechous phyllotaxy.